So let me get started on the multilingual learning part. This is kind of something that I put at the end because it seemed less important to me at the beginning when I made the syllabus. But as this semester has progressed, it's actually seemed to become more and more important. And in fact, many of the kind of state-of-the-art results for a lot of the tasks that we're doing here are using some sort of multitask learning or something like that. So I think it is this is worth paying attention to if you want to get good numbers on whatever task you're interested in. When we're talking about multitask learning, we need to remember that neural networks are feature extractors, so they create some sort of vector representation of sentences or words for use in the downstream task. And it could be a single vector representation for the sentence, or it could be a single vector for each word. But we might create those single vectors using a complicated encoder or something like that. And in many cases, we can use the same representations in multiple tasks. So for example, word embeddings are one example that we talked about at the very beginning, which is where we use some sort of other training objective to get good representations for words and then use that in a downstream task. That was the only thing I talked about then, so I'm going to talk about some other options here now. And in terms of types of learning, just to kind of get the terminology clear on the things that I'm going to be saying, multitask learning is basically a general term for training on multiple tasks. The definition of task can be a little bit vague. Transfer learning is a type of multitask learning. And transfer learning is basically where you care about one of the tasks more than any of the others. So you might train on multiple tasks, but you only really care about a particular one of them. And domain adaptation is also something that you will often hear in natural language processing. This is a type of transfer learning where in general the output is the same. We're outputting the same thing like a translation or tags or something like that. But we want to handle inputs that come from different topics or genres, etc. So these are kind of the definitions that I'm going to go by as I explain further. Yeah.
So the reading seems to be quite multi-objective learning and multitask learning.
Uh-huh.
The examples provided the task is a single task where multiple objectives to optimize.
Uh-huh.
So are they the same thing, or is one complex or the other?
So multitask learning, in my point of view, doesn't necessarily need to have multiple objectives. Although, let's see. Yeah, it's kind of hard to say whether there's really a difference between them or not. You know, if you think about your objective or your loss function or whatever, in most multitask scenarios, you're going to have a different loss function. It might not have a different form. It might still be machine translation loss, but you could split it up into your loss function defined over different domains. So I guess multitask and multi-objective are pretty similar, unless somebody wants to disagree with me. No? Okay, nobody's disagreeing. So I guess they're probably similar things, especially from the point of view of neural networks. Yeah.
I think the difference lies in evaluation. So if it's multi-objective, we'll probably evaluate two different things using something like blue score when it comes to machine translation. But if it's just multitask, we just train it to have that higher likelihood for both the tasks. So although in practice it ends up being the same thing, but it depends on how you're evaluating the two things.
Yeah, so actually now that you mentioned it, there is multi-objective optimization where your output is the same, but you want multiple objective functions to be high, and that's a different thing. Basically, it might have a single task like machine translation, but you want both your BLEU score and your meteor score to be high, as opposed to just one of the two being high. And that's something completely different, actually. So yeah, so that's a good point. I agree now that they are probably they mean different things if you're talking about multi-objective in that particular way. So, and that's something I'm not going to cover at all here, multi-objective optimization. So, okay. So then the question about when to multitask, basically there's a bunch of different tasks in NLP. So just for your assignment or whatever, your project for this class, you had a list of 20 tasks that you could choose from, and many people didn't like any of the tasks in the list of 20 and decided to do something completely different. So there's obviously a lot of tasks that we can do in NLP. You can kind of split them up into the type of data source that you can train them from. And things that can be trained from only text are language modeling, mostly. Things that can be trained from naturally occurring data, machine translation. So these are the ones where we don't need NLP researchers to create data for us. Somebody else will go and create lots of data for us, so we don't need to bother making it. And usually these have much more data than the ones where we need to create data. And then finally, we have hand-labeled data things where we need something like the Pentry Bank or something like that, where we actually have to have linguists or NLP researchers go in and label things. And we have each of these in many languages, each of these in many domains. So which tasks do we want to combine together? And this is actually something that surprisingly wasn't covered in the reading, although perhaps it might be obvious. So what are the ideas? Which one should you use? Anybody? Oh, so okay, if you want to do multitask training, which tasks should you use for multitask training? Like, okay, let me be more specific. If we want to do multitask training for summarization, where we want to output a summary to text of text given a document, what task should we use for multitask learning? Yeah.
Anything that makes the objective function smoother, heuristically speaking. So something like language modeling would make the objective function smoother and make it simpler for the model to converge by first learning the language model easily and then proceeding from there to...
It depends how you quantify smoothness. I don't know if it's a forgiven conclusion that the objective function becomes smoother because you're using a language model, but maybe easier to learn, maybe yes, yeah.
In NLP, don't we usually have task hierarchies and maybe some in the cross-stack with a lot of tasks? Maybe it's useful to divide your task into like the simplest thing and then something that's
That's a very good point, and maybe I'll talk about it later. So maybe we want simple tasks first, and then we want to try harder tasks. Any other ideas? Yeah.
Maybe having auxiliary tasks that retain the outside information could help, say, the auxiliary task to do the auto encoding input or something like language model, which probably captures the input distribution of data pretty well.
So something like language modeling, so either something that captures the input distribution or something that ensures that our representation maintains all of the information in the input. Yeah, I think those are good. So I guess my rule of thumb number one is that we should try to increase our data. When we want to do multitasking. Especially when we want to do transfer to a specific task, it's not as useful to train on a task where we have much less data than the task that we care about. So if we want to train on both parsing and machine translation at the same time, we can get much more data for machine translation. So training on parsing, training a machine translation system, then using it to do parsing will probably give you a bigger gain than training a parsing system to help your machine translation. So in general, if we have a specific domain that we're interested in, we'll want to use lots and lots of data from the general domain because this increases the amount of data that we have. If we want to do a low resource language, for example, we might want to do training on a high resource language where we have more data. If we want to do something where we require hand-labeled text, it's probably a good idea to use plain text or some sort of naturally occurring text than other things. Yeah.
So in the case where there's a difference in the amount of data available, right? Wouldn't at least for the shared layers, wouldn't the parameter updates be sort of biased? So do we want to also weight loss function somehow?
So the question was, if we have more data in one of the tasks, wouldn't that bias our parameter updates? And yeah, sure, I'll talk about that in a little bit. So this is a general rule. If you're thinking about doing multitask learning, it will be most effective if you go from high resource scenarios to low resource scenarios. And it kind of makes sense, but I've seen multitask learning papers that weren't really thinking about this as much. So I think it's a good idea to think about it. There are examples where you can go from a parser to improving machine translation, for example. But in almost all of these cases, they take a pre-trained parser, they parse all of their machine translation data, then they do a kind of joint learning thing where they try to use the machine translation model to both predict the parses and the machine translation output. So in that case, they're kind of like creating pseudo data. They're doing self-training on this automatically parsed data and hoping that that biases the model in the appropriate way, which that does seem to help, but it's not straight up multitask learning with labeled data. And it probably won't, if you do something like that, it probably won't increase your parsing accuracy, at least not very much if you have a good model already. Okay, so my rule of thumb number 2 is, this was kind of this is very hand wavy. It's not saying you make the loss surface smoother. It's not saying you need to encode all of the information, but it's saying make sure your tasks actually are related in some way. So you don't want to do something that's completely unrelated, which also makes sense, but sometimes people aren't necessarily thinking about this or don't necessarily explain this in the introduction of their paper. And it seems like you kind of arbitrarily threw stuff together. So one very interesting example of this, it was a very kind of like cute example that might not be very practical, is there was a method for predicting eye gaze and also doing summarization at the same time. So the idea is, as people read text, they tend to focus on the more important content. So they put eye trackers on people, and they had them read text, and they trained an LSTM to both do summarization and predict where people were looking. And it actually works really well in just straight up multitask learning, where you try to predict both at the same time. So I thought this was a very creative way of coming up with like tasks that were related. And I think this won best short paper at NACL or something like that, because it was well motivated. So when you're doing something like this, just make sure, like, should these tasks share the same kind of information? I think if you could quantify that in some way, like whether it makes your objective function smoother or like some other property of the distribution that you could come up with, that would be even better than just going by this intuition. But future work. Okay, So let me move on to methods for multitask learning. So in standard multitask learning, this is where we actually literally have two different tasks, and we want the model to do well on both of them. So we don't particularly care about a particular task more than the other, and we want to get both. The standard way of doing this in neural networks is we have something like a shared encoder, and we use the encoder for both tasks, and we train on both translation and tagging. And in general, it's as simple as randomly choosing mini batches from one of the multiple tasks, and then maybe having a separate decoder for each of the tasks. And there are many, many examples of people doing this, starting from Colabert and Weston, which was one of the first major recent papers on neural networks for NLP. And then you read a whole survey of all of the things. So if you find your favorite task in that list on the survey, you can find an example of somebody doing multitasking on it. There was a question before about when the big data overwhelm the small data. And the way we normally prevent that is just by randomly choosing mini batches according to some schedule. So we might even if the translation data is much bigger, we might randomly choose mini batches with a 50% probability from each of the tasks. And of course, you can adjust that probability however you want, et cetera. It's also common if you're doing multilingual training to upsample the less popular languages to make sure that you get the same number of mini batches from each language. Any questions about that? Okay. Then the next one is pre-training. This is what you do when you want to do transfer and when you actually care about one of the tasks more than the other one. So first train on one task, then another, like this. So train on translation and then do tagging. This is most widely used in word embeddings. So Turian et al. In 2010 showed that this is an extremely useful way of doing transfer to a bunch of different tasks. And I think they evaluated it on 3 or 4 different tasks and showed that word embeddings were useful there. Also, one thing that has been very, very effective recently, and is actually one of the reasons why I'm thinking that this is more and more important, is because this has been very useful in pre-training sentence representations as well, whether these are representations for single words in the sentence or for the whole sentence itself. So examples of pre-training encoders. It's common to use language models. So language models are by far the most popular way of doing this. The reason being that you can get nearly infinite language modeling data. You can get so much data in English that your GPU will not be able to see all of it before more English data is made. So you can get it as much as you want, which means you can learn very good representations from this. Also, translation models. So there was a nice paper that basically trained a translation model and used the vectors learned by the encoder of the translation model as representations of words. And basically this method showed that this translation model did better than language models. And then shortly after that, a new paper came out that said bidirectional language models are better than translation models for learning this kind of thing. And now, for the next month or so, probably this will be the state of the art, and then it will switch to something else. But basically, the idea here is that you just train a language model going forward on a particular a forward language model predicting the next word, a backward language model predicting the word backwards, and then concatenate both of them to get a representation of a word or a span or the sentence or whatever. So if you want to get better results on your task, I would highly recommend taking whatever LSTM you're using in your model or whatever, and just pre-training it on a lot of data. You can also, I actually missed writing this on the slide, but it's also very effective to pre-train the decoder of a sequence-to-sequence model. So if you're doing a sequence-to-sequence type task, you just pre-train this sequence-to-sequence decoder as a language model, and then stick it in and use that in your sequence-to-sequence model. There was a good paper at EMNLP on doing this for machine translation. And if you can't find it, then email me and I'll send you the paper. Yeah?
The first language model refers to unidirectional. Does that refer to unidirectional?
Yeah, this first paper was unidirectional. I think it was anyway. Yes.
Is there any experiment done by bidirectional, which is
Well, this translation model was bidirectional, but I think the main thing was just that this gives you way more data than you can get translation data. So, and it's much easier to get data in the domain that you care about. So, if you limit yourself to translation data because the middle paper said it was better, then actually you might lose in either amount or domain specificity of the data. So that, because of that, I think bidirectional language models are a good choice. Yeah.
But even for translation models, people pre-train with language models.
Yes, it actually wasn't that common up until now because you can get a lot of translation data anyway. So pre-training the language model wasn't helping a whole lot. But there was this nice paper at NLP that showed this was very effective. So I think more people might start doing that. Okay, so one important thing to remember about pre-training is actually if you don't do some sort of regularization, pre-training won't help you at all. Theoretically won't help you at all. And the reason why is, or won't help you very much. And the reason why is basically because if you pre-train and then you run your model and then you train your second model on a different task, it will basically just forget everything that it learned during the pre-training process. You know, it will move the parameters into a totally different part of the space. So you need some sort of regularization to prevent this from happening. And in order to do this, the most obvious one that you probably are doing without even thinking about it is early stopping. So if you pre-train your models and then you run training on a different task and do some sort of early stopping, you are doing a type of regularization. In fact, you can kind of show that this that early stopping is a form of implicit regularization that's preventing your parameters from moving too far. So this is often enough to keep the parameters in a good place in the space and ensure that pre-training works well. You can also do something like explicit regularization. So explicit regularization is you do something like L2 regularization on the difference between the from the initial parameters. So if we define our adapted parameters as the pre-trained parameters plus this difference from our initial parameters, then we can take our regular log likelihood objective and just add the norm of the difference, the L2 norm of the difference on into our objective function. And this will prevent us from getting too far away. And of course, we need a constant here. Sorry, I forgot the constant in the equation. So this would actually be extremely strong regularization that you would never want to apply to your model. But if you add a constant and adjust it, you can keep things in the right part of the space. Another thing is if you do dropout and combine this with early stopping, this is also a form of regularization. And there was a paper, the Barone et al. Paper. They investigated different ways of basically fine-tuning your model for machine translation. And what they found was, interestingly, dropout and early stopping were enough to kind of ensure that your model is appropriately regularized. And this is really good news because dropout and early stopping are both extremely easy to implement, while the middle one is actually a bit more difficult and slow. So I think if you read this paper and look at their recipe, then that'll be a good thing to follow. And another thing that you can do is kind of selective parameter adaptation. So this is one form of regularization that's super strong regularization, essentially. It's saying, do not update certain parameters, but you can update other parameters. So it's like infinite regularization on the non-updated parameters and non-infinite regularization on the others. So for example, in cross-lingual transfer for neural machine translation, this paper examined the best parameters to adapt. And basically what they found was it was a good idea to adapt everything but the target, the target embeddings, where the target embeddings were the ones that we needed to, the target embeddings were the ones in the language that we, in the English language. So don't update the English embeddings, but update every other parameter of the model, essentially. And this was, this seemed to give them the best results. Yeah.
How well does L1 work in practice? Especially if the model has, we expect the model complexity to be, does it help a lot?
How does what help?
L1
L1 or L2. I haven't used L1 very much because L2 is smoother and it seems to, it's easier to optimize with your standard libraries. But L2 doesn't actually work trivially. I've had a lot of experiences where it doesn't work super well. And when it does work, you need to give it an extremely low coefficient. In general, dropout works better in my experience, but I definitely have seen people using L2, and I assume that they tried various things and that seemed to work for them. So you definitely do see people using it, but I myself have had much more success with dropout, I guess. Has anyone succeeded with L2 before? Has anyone succeeded with dropout? So that's a pretty good vote of confidence for dropout.
A lot of the standard libraries inherently have some amount of L2 regularization.
Like on by default?
It's called rate decay for some of the optimizers.
Yeah. So weight decay and L2 are essentially similar. Yeah, it depends. Some might have it on by default, some might not. Dynet used to have it on by default. Now it's not on by default because I've found that having it on by default is actually not a good idea. Number one, because people don't realize it's on, and number two, because sometimes it hurts and it often doesn't help. So, but if you have a weight decay thing that you can use, you can definitely try it. And that's an essentially free way to add regularization to your model also.
Also, weight decay and L2 are not always the same complicated optimizer.
Right, and if you have a complicated optimizer, weight decay and L2 are not the same. Weight decay and L2 are only the same if you're using SGD, or if whatever particular, if you're using simple SGD, or if whatever particular optimizer you have implements it correctly. And implementing it correctly can be very slow for a lot of optimizers. So yeah, it depends, I guess. Okay. So then another thing you can do is soft parameter tying. So this was covered a little bit in the reading, but basically you share parameters loosely between the various tasks, and the parameters are regularized to be closer but not tied in a hard fashion. So the example from this paper is basically you have things like the hidden layer, you have embeddings for part-of-speech tags, arc labels, and the softmax layer. And the part-of-speech tag, arc label, hidden layer, and softmax layer are all kind of regularized, so the parameters get to be close together. the words themselves, because this is a multilingual parsing task, the words are not made to be the same because you'll have different words in different languages. Okay. So now I'm just going to go through a couple examples. These also might be things you want to think about for any research project that you're doing, just because doing a little bit of these things can often give you significantly better results and a stronger baseline or whatever to work with. So for domain adaptation, you have basically one task, but a lot of the incoming data could be from a very different distributions. So you have like news text, medical text, spoken language, and then you want to translate all of them appropriately. Often we have a big grab bag of domains. So we have all of these domains, but we care in particular about a particular one of them, like medical. And there's basically two settings. One is supervised and one is unsupervised adaptation. So for supervised, we have data in the target domain. I'll talk about all of these in turn, but the most common way, which actually works quite well, is supervised pre-training on large data and then tailoring to domain-specific data by just resuming training. Another thing I forgot to mention is often when we do pre-training, we restart training with a smaller learning rate than we had for the original one. To keep things from moving too much. That's another way of regularizing your model. But this paper by Long et al., they did this, and this gave them a huge gain in machine translation related stuff, by like 7 blue points, which is a huge amount. Also, you can learn domain-specific networks or features. I'll talk about this in a second. And for unsupervised adaptation, we have no data in the target domain, and we want to match the distributions of the extracted features, for example. So supervised domain adaptation through feature augmentation. The one way we can do this is train general and domain-specific feature extractors, then sum their results. So this paper, basically what they did is they had one LSTM for each domain, and one encoder for each domain. And basically, the domain encoder would encode the sentence, the general domain encoder would encode the sentence, and then you would add the two representations together. And the reason why this might be a reasonable idea is because the general domain encoder will basically extract most of the stuff you need, and then the domain-specific encoder basically just has to find all the other stuff that is specific to the domain. It doesn't have to find, just things that will work anywhere, but it can find the specific, domain-specific features. Another way to do this, which is much easier, is we append a domain tag to the input. So we add the word news, the tag news before we get our news text. We add the tag medical before we get the medical text. And hope that things will work out. This actually works really well for sequence-to-sequence tasks. It will probably also work for parsing or part-of-speech tagging tasks. And the reason why is simply because the model now knows I need to, create the context-specific representations that are specific to this domain. So if it's already seen the news tag and it gets something that's translated in one way in the news text and another way in the domain text, in the medical text, then it will be able to discriminate between them. Yeah.
What was the task?
Oh, this was for machine translation. But I expect it will work in most structured prediction tasks. I think it would also work pretty well in classification tasks even, because if you think about it, you're telling it beforehand, before it starts doing any of the encoding, look out for the things that are important for this domain. You don't need to pay attention to those.
This is similar to the Google NLP, the zero-shot one. It also appends language specific.
Yeah, so the Google NMT one is on the next slide, and it's doing exactly the same thing. So the first paper to do this actually was doing tags for politeness in machine translation. So they just added the tag that said translate this in a polite way, translate this in an impolite way. That's also a type of, I don't know, domain or style adaptation, I guess. And that also works, yeah.
For the first one, do you know how is it related to the frustratingly easy domain adaptation?
So this is actually called Frustratingly Easy Neural Domain Adaptation, or the paper. So it's very much inspired by the Frustratingly Easy Domain Adaptation paper, where you basically just add domain-specific and domain-independent features. Yeah.
Would it be a better idea to add the tag representing the domain in the function that is generating the attention rather than to the entire representation?
Sure. You could try that as well. The good thing about having this in the encoder is that if you're running like several layers of BiLSPMs in your encoder, then it will just automatically be able to kind of give that, or if you're doing self-attention, for example, it would automatically be able to kind of modify the representations of all the other words in the text based on the existence of this tag. So it might have exactly the same effect. But you might be able to be more parameter efficient by just modifying the attention also. So that might be something worth it. Anything else? Okay. So the next one, this is actually maybe a bit more interesting. From my point of view, it's kind of elegant and beautiful. But the idea is unsupervised learning through feature matching. So the idea here is particularly in things like image processing models, you can think of a big, deep convolutional neural network that takes in the image in the first layers, and then it extracts gradually more kind of semantic features in the later layers. And the idea behind this is basically you take your initial CNN, and you have a few frozen layers that are basically like your edge extractors or whatever, and these are constant between all of your domains. Then you have a few layers that you just fine-tune during training. Then you have a few layers at the end where you run your images from one domain, and you run your images through, you run your images from your labeled training domain, and then you run your images from your unlabeled target domain, and you try to ensure that the distributions of the features match. And this is using a method called multi-kernel mean maximum discrepancy. It's a kernelized training method that tries to minimize the discrepancy between the representations learned. So can anyone guess what happens in 2016? No? Yeah, GANs. Exactly. So I think 2015, the reason why this didn't use GANs is because nobody used GANs in 2015. Now, basically, you have an adversarial network that tries to discriminate between the features that were extracted by one domain and another domain and prevent them from being distinguishable. And I think this is a bit easier than multi-kernel learning. I don't know which would be more stable, so, but both of these have had have a good effect. Okay, so now I will move on to multilingual models. Are there any questions about adaptation? No? Okay. So multilingual, I'm going to separate these into multilingual inputs and multilingual outputs. So multilingual inputs is often relatively simple. Basically what we do is train a single large encoder for both of the, all of the languages. Optionally, we can also use an adversarial objective to help ensure that the information is shared between the two. So I showed this during the adversarial thing, so I won't go into too much detail. But basically, we have a feature extractor where we have word embeddings, and then we run this through several encoding layers. And by the time we've extracted the representations, we want it to be able to classify sentiment, but not be classified by its language. And this is quite successful in a number of tasks. We've seen that this really tends to help. The more difficult thing is multilingual structured prediction or multilingual outputs for sequence-to-sequence models. And this, I don't think there's a consensus that this is really helpful yet. People have tried to make this work, and we haven't seen really huge gains. But basically, things are harder when predicting a sequence of actions or words in different languages, just because the predictions are very different. So one simple method to do this is add the embedding of the expected output to your model. So you can add the embedding at every time step. I believe this paper by Yulia Svetkov was the first to kind of try this, but there might be others. This was for language modeling. So they had a gating function that basically selected the information that was useful for a particular thing. And then maybe the easier way to do this, which might be as effective or maybe not as effective, is the is the method like this, where we have if we have this as an example and we want to translate it into multiple languages, we add a token at the beginning, French or Japanese. This was developed almost entirely simultaneously. In other words, like within one day of each other by two groups. One was Alex Weibel's group and one was the Google group. And the details are slightly different. In the second paper, they're actually learning a different embedding for the words in each of the languages. And I think learning a different embedding for the words in each of the languages seems to help a little bit, but I have not experimented with this extensively. Interestingly, this allows for zero-shot learning. So zero-shot learning is basically where you have data for French English and Japanese English, for example, but you could use it to translate between French and Japanese. So you train a French English system, an English French system, a Japanese English system, an English Japanese system, and then you just take in a French input and say translate this into Japanese. And this doesn't work very well. It kind of works. It gives you something that looks like the appropriate target language, but it really, without extra training data, you don't get great results here. You could think of zero-shot learning for other tasks. So people have only really done this, I believe, for or it's mainly been tested in things like translation, but you could think French English translation is one task, Japanese English translation is another task, but you could take any other two arbitrary tasks that you want and try to do zero shot between them. I'll let you be creative in thinking of the tasks that you could do that with. So zero-shot learning doesn't work very well as is. So, but zero-shot learning has an advantage in that if you have like 50 language pairs or 50 tasks, you can learn a single model that will perform all of them for you. So this paper is a recent paper from ACL that actually has a pretty interesting idea, which is one other way to do this in translation specifically is pivoting. So you first translate from French to English, then you translate from English to Japanese, and you can essentially make training data that allows you to translate between multiple languages. And so what they did was they created a teacher network that basically uses this pivoting method to calculate the probabilities. The probabilities of generating a particular output, and then they use this model to teach a zero-shot learner, or to teach a single model to translate between all of the languages. And they had significantly more success in training a single model that works on lots of languages than if you tried to do it without doing this. Okay. So any questions about stuff so far? No? Okay, so finally I'll move on to the multitask models. Unfortunately, there's just too many instances of this to cover all of them, as you saw in the survey. So I encourage people, if you're interested, to take a look at all of the things in the survey about the particular task you're interested in. As I said before, the most common is to train on plain text or translated text and use the information to improve the accuracy of another task. You can also train on multiple annotation tasks. For example, training with multiple annotation standards or training different layers for different tasks. So I'll just cover these very briefly. So this is something that you might not normally think of for multitask learning, but basically it's the same task, a bunch of different disparate annotated data. So for example, for semantic parsing, there's basically 3 different common annotation standards for how to create meaning representations. So the idea is you just train on all of them. Similarly, for Chinese word segmentation, there's a bunch of different ways you can define a word. And each of these has a different annotation standard. And there's another, the reference has disappeared from my slides, but I think it's on the reference list, so you can take a look there. Another really interesting paper, this is not an NLP paper, but I kind of like it, is there are, very often you will have multiple annotators that annotate different pieces of data. So let's say you have data that's generated by, okay, in this particular example, they had labels created by doctors for medical data. And this was a very difficult task even for doctors, so the doctors gave kind of disparate labels. So they trained a different softmax to basically predict what each doctor would say, about that particular image. And so now they have a single model that shares the kind of like feature extraction stuff, and then different softmaxes to predict the decision of each of the doctors. Then what they do is they ensemble all of them together, and in the end use that ensemble decision as the final decision. So they basically train a committee of doctors, and then they have the committee discuss the result and make the final decision. And I believe this ended up being a better predictor of the committee than any of the individually trained models or something like that. So I think this is nice. Especially, a lot of people are going to be dealing with annotator error or something like that. So this would be a good way to handle it. Another kind of interesting idea, I'm not sure how much I buy this, like whether this is really like necessary or not, but it might be worth trying if you're thinking about these things, is basically you have these multiple levels. So this was exactly the idea that we had before, which is where you have part of speech tags in your first level, then you have chunks in your second level, then you have syntax, then you have semantic relatedness, entailment, etc. And each of these is kind of a different level in your encoder, and you train the earlier levels to do the lower level tasks and the later levels to do the higher level tasks. You could also argue that you can just train one big deep decoder and it would do just as well, but I don't know if that I don't know if that's the case with that. So this paper just came out recently, so I think there's more examination to be done in this particular task. But I think it's a cool idea if it does end up being important.
Why does it have 2 different models and then the
So these are actually the same model. This is just to show that when you have sentence pairs, you might want to run two. Okay. So that's all I have for multitask learning related stuff. Are there any final questions? Or? Yeah.
The result of statistics that say if you add variables to your statistical model, then the model codes will automatically improve regardless of whether those variables are linked or not. It's just not a fact of how the model that it's included. So I wonder whether something similar is happening here. Whether adding another task or another feature or variable is really helpful, or it's just an artifact of how the optimization is done.
I see what you mean. So like if you add, let's say you're doing a linear regression, and if you add variables, you can automatically explain more of the variance. I don't think that is related to multitask learning in this sense because you're not adding more input variables. It would be more, I believe it would be more relevant to multi-source, like if you wanted to take in a single sentence or multiple sentences and then use the multiple sentences to try to predict the output. That would be like adding things to your input. I think that is not related to multitask though here because you're predicting the output and your inputs do the same. Yeah.
At what point does multitask learning cross over into the domain of transfer learning and vice versa?
Oh, so I gave the definition at the very beginning, and transfer learning is multitask learning where you only care about one task or a subset of the tasks. In the other tasks, you don't mind if your model gets worse on those tasks. And then multitask learning in general, you'll often care about the results of all of the tasks. Okay. Well, thanks a lot, everybody. It's a little bit early, but I'll try to, if you have any questions about projects or anything, I'll try to answer those as well.